What we've been doing so far is explicit differentiation. It's when one of the pronumerals, and normally we make it y, is the subject. Implicit differentiation is when we don't actually have to just make y the subject, we can still differentiate, and it uses our chain rule idea in order to do it. I'm going to do this explicitly, but showing you where it comes from implicitly, because I mentioned this the other day, but what we're really doing is differentiating both sides. Now again, we don't actually write this down, but what we're doing is we're saying, hey, I'm going to differentiate y with respect to x, and then on the right hand side I'm going to differentiate x squared with respect to x, and that's when we go, well hang on, and this is the implicit differentiation part, I can't differentiate y with respect to x, but I can do it with respect to y. So I'll differentiate it with respect to y and then multiply it by dy dx, so like the dy's cancel if you like. Well, differentiate y with respect to y, you get 1, and then on the right hand side when we differentiate x squared we get 2x, and there's our answer, which of course we would have written down in one line, but that's where it comes from. But that idea, if we carry it through, I could now differentiate this without actually having to make y the subject. X equals y squared. Same idea. I'll differentiate both sides with respect to x. But on the left-hand side, that's not a problem. Differentiate x with respect to x, I get 1. But on the right-hand side, I've got a problem. I can't differentiate y squared with respect to x, but I can differentiate it with respect to y and then multiply it by dy dx. And so that's what I'll do. Left hand side we just get 1, right hand side we get 2y times dy dx. I come up with an expression for the derivative. The difference is it's in terms of y instead of in terms of x. That's not a big deal. And actually, if you think about the curve, that's more useful. X equals y squared is a parabola on its side. Now, if I wanted to find the slope at, say, whatever that point is, oh, well, 1 would be on there, wouldn't it? Let's say I wanted to find it at 1. Now, if I was to substitute in x equals 1, I've got a problem, because it's not a function. So I end up with two possible answers for x equals 1. How do I know what the answer is going to be? But if I differentiate and get 1 on 2y, I'm now substituting in the y value. Y value of 1, there's only one possibility now. And I can get the slope by using the y value instead of the x value. That's one of the advantages of using implicit differentiation rather than making y the subject of that. If I had to differentiate this sort of expression, x squared y cubed, okay, I'll just use the product rule. Write down the first, x squared, diff the second, y cubed. Hang on, I can't differentiate y cubed with respect to x, but I can do it with respect to y, so that's what I do. 3y squared, but to balance it out, I'll multiply it by dy dx. Plus, write down the second, y cubed, diff the first, that's not an issue. 2x. There's my derivative. It looks a bit unusual, but that's the derivative. Now imagine I wanted to do this then. I've got a circle and I want to find the equation of the tangent. Differentiate it. The beauty of implicit differentiation. I don't have to make y the subject. I'll just differentiate everything with respect to x. Well, x squared, that's not a problem. 2x. Y squared. Can't do it with respect to x, but I can do it with respect to y. So I'll get 2y multiplied by dy dx to balance it out equals, on the right hand side, differentiate 9 with respect to x, I get 0. I can play around with that and I have a derivative. This time I have to substitute in both the x and the y value. Think of what the circle looks like. That's now useful because if I was to just substitute in an x value, well then I've got two possibilities. If I was to just substitute in a y value, I've got two possibilities. But here, I substitute in both the x and the y value, I've only got one possibility. I'm going to get the answer that I want. And let's work that one out. When I substitute in the point 1, 2 root 2, there it is, minus 1 over 2 root 2. I have a point, I have a slope, I can find the equation of my tangent, and there it is, x plus 2 root 2y minus 9 equals 0. So that's our idea of implicit differentiation. Now our textbook doesn't have an exercise, but the old Cambridge textbook did, so I've copied that in there and got some questions from there.